everybody, in this tutorial we'll see how to analyze urban greenery changes over the period 2017 to 2025 using Google Earth Engine and the Sentinel-2 Harmonized satellite imagery. This step-by-step guide walks you through time series analysis to detect and quantify vegetation dynamics and urbanization impacts with high-resolution cloud mask data. We leverage the Sentinel-2 Level 2A Harmonized datasets, which provides atmospherically corrected multispectral imagery at 10 meters spatial resolution, which is ideal for Landcover and vegetation monitoring over large areas. You can note that there are also more advanced and complex methods for conducting multispectral and Landcover analysis at ultra-high resolution, archiving results down to the centimeter level. So if you're interested in exploring those techniques, let me know in the comments and I'd be happy to create a video on that topic too. Of course, don't forget to subscribe and let's get started. In the first step, we define the study area, so we start by adding the study area boundary, which is in this tutorial the RANS polygon that is located in my assets. But if you want to draw a polygon on your map, you could do this too. So my polygon is here in my assets. I can close it and rename my study area around. So to add this new polygon, we can use the function map_add_layer with styling parameters that will set the outline color and transparent fill. So this is the function map_add_layer. Okay, so you can run this code and you will see the polygon of the AOI that have just been appeared. So this is RANS, which is located in northeast from Paris in France. You can add the function map center objects that will zoom directly on your AOI when you run the code. In the second step, we load the Sentinel-2 Harmonized image calculation using the function image collection. We will filter this collection with function filter bounds to only include images covering rounds. We can filter this collection spatially with the function .filter bounds with the AOI to only include images covering rounds, so the AOI. Then we will apply a temporal filter with the function filter date to select images from 2017 to August 2025. And finally, we will filter out images with more than 20% cloud cover using the function cloudy pixel percentage. The step 3 will involve cloud masking. So to mask clouds, we will define a function mask clouds that uses the QA60 bounds, which contains cloud and cirrus flags encoded as bytes. We apply bytes-wise operation to check these bytes and create a mask where cloud pixels are excluded. If you wonder what is QA60, it's a quality assurance band in Sentinel-2 Level 2A imagery. It is a 60-bit band that stores bit flags about clouds and cirrus clouds in the image. Specifically, the bit 10 indicates clouds and the bit 11 indicates cirrus clouds. It's the most thin high-altitude clouds. So this expression means shifting the number 110 bits to the left, so it gives the value 124, which targets bit 10. So this function will isolate the cloud bit. This allows us to check if the clouds bit is equal to 0, so basically there is no clouds. And here the same logic is applied to cirrus detection. So if those two conditions are combined, the pixel is kept only if neither clouds nor cirrus are detected. Here you will basically apply the mask, so it will set the pixels with clouds or cirrus to be transparent. They will be masked out. So here we create a function to compute 3 spectral indices for each image. So the NDVI, the normalized difference between near infrared, so the band 8, and the red band, so the band 4, indicating vegetation health. Next, the EVI, calculated with a formula using near red and blue bands that are designed to reduce atmospheric effects and improve sensitivity in high biomass regions. And finally, the NDBI, the normalized difference between shortwave infrared, the B11, and near the band 8. So basically this index will highlight build-up areas. So the three indices are added as new bands to each image of the collection. So let's create those indices. Okay, so once we created those three indices, we can create annual composites. So we will generate annual mean composites for each index by iterating cover of each image over the years 2017 to 2025. So it means that for each year we will filter the image collection by date, compute the mean with the function .mean, select the indices bands, then clip to the AOI geometry, and set metadata properties like year and time start. This results in a collection of annual summary images. So we will start by defining a new variable, so years. We will list sequence of the period of the study. So this is it. Then we will set the annual stats. So this code basically translates what I just said. So I've created a start variable and an end variable, and basically it will take all of the images per year, and we will apply a mean function to all of those images and select the three indices, clip with the AOI, and this is for the analysis, for the plot chart analysis. So we'll see this together after. If we want to print the number of images per year, we can create this new variable. So just wrote it earlier. So it will print in the console here while we have run this code how many images are available in each image collection. Basically it's a new chart that will display the year and the images count per year. So in the step 6 we visualize NDVI and NDBI for 1 year. For example, the year 2024. So to visualize it, we define visualization parameters with color palettes and ranges for NDVI and NDBI. We filter the annual composite for this year, or for 1 year in particular. So we use the function e.filter.aq and add the NDVI and NDBI layers to the map with the function map_add_layer. So this is a really simple portion of code. So I did a test earlier, so I set the ranges between those values, but maybe you will have to adjust it to your AOI. So don't hesitate to ask me if you have some issues with that, but it will fit with the most of your biomass and urban analysis. So in the step 7 we will generate the NDVI and NDBI time series chart. We will use the function ui.chart.images.series to create time series charts of the mean annual NDVI and NDBI values over the area of interest. So the charts will take the annual composites, reduce them spatially with a reducer.mean function, and plot the results with labeled axes and titles. So this is how you can do this. So you set the indice, you set the area of interest, you apply a reducer, and you scale with your spatial resolution. So here for this tutorial it's 10 meter resolution. You can print and set the title, the axis with all of the parameters you have. So you do this for the NDVI and for the NDBI, those two indices that will help us to generate the Landcover changes detection. Oops, I forgot one step. So the step 8 will help us to create an NDVI linear trend, so with a regression. So this helps us to detect the NDVI, the loss of NDVI and the gain of pixel of NDVI over the urban area. So basically you will see in red you will see the loss of NDVI, and in dark green and white you will see the zones that are mostly covered by vegetation over the urban area. After this step, we will be able to create the Landcover classification. So we will have to define thresholds to classify pixels into vegetation, buildup, or other classes based on NDVI, NDBI, and AVI values of each pixels. So we will use a function that will create Boolean masks for vegetation. So for example, when the NDVI pixel are greater than 0.3, so when the NDBI are greater than 0.05 and low AVI, and assigns integer labels accordingly, and the classified images will be stored with their year metadata. Here I made some tests before recording this tutorial, so those thresholds are basically good for my area of interest, but you may have to adjust on those thresholds here for each indices. So we use this function like I just said, and we have 3 variables for each functions, and here you will compute those thresholds to classify each images in the image collection. So you may need to compute percentage for each Landcover class, this code that will allows us to display the Landcover classification. Maybe you want to plot Landcover evolution bar chart. So the chart will basically plot percentage of vegetation buildup and other areas that have been classified. It will allow us to visualize Landcover changes over time. Okay, if you need the code, of course, I shared it on my GitHub, so you will see the link in the description of this video. After that, you will display Landcover classification. It will show vegetation and build-up area for the year 2024. And maybe you want to detect year-to-year vegetation changes, so we could compare classified images year by year. So for each year starting from 2018 we get the previous and current year's classified images, and we can identify pixels that gain vegetation or lost vegetation. So we can create change masks and store them as bands with year metadata. So this is actually how you can do this. So you create a new variable, I called it changes, but you can call it whatever you want, and you will be able to visualize the loss and the gain of vegetation in urban area. Finally, of course, you want to display vegetation gains and losses. So basically we will see pixels that will be generated in red for losses and in green for gains of vegetation. Okay, so we can run this code finally. So after a while you will see that you have your Landcover classification. So in green you see the vegetation, and in black you will see the build-up area. If you want to display the vegetation gain in 2024 or the losses, you can of course activate those 2 layers. So you see the high resolution detection of pixels of vegetation, losses, gains, and build-up area. You can of course enhance these methods using ultra high resolution image collections And of course you can use AI or algorithm to vectorize perfectly all of the area, but here our goal was to analyze a large area. So we see that after the year 2023 we have a significantly evolution of NDVI, for example. And finally you have the Landcover, evolution, vegetation, buildup and others. So you can display this bar chart and you can download the CSV or maybe the PNG like you want. Of course you can visualize the other, so for example the NDVI trends. So this is this NDVI trend that have been used for each image collection to classify the vegetation, for example. You can see the NDBI 2. This is this indice that have been used for the build-up areas mapping and recording. So we have those two indices, and here of course you have the NDVI of 1 year. So those indices have been used for the classification of the losses and the gains of vegetation of urban area of arounds. So you have here to remember the classes of the year 2024, but you could do this for each year and generate those plot analysis by using Google Earth Engine. So I hope this tutorial have been helpful. Don't forget to subscribe. Good luck for your Google Earth Engine project and see you in the next videos.